Hello friends. So today we are going to solve few questions, and these questions are from the year 1978 and 1979, 1981, and we have from 1982. From 1978 we are having three questions. From 1979 we are having two questions. From the year 1981 we are also having three questions, and from the year 1982 there are also three questions. So total we are going to solve these 11 questions. So in the first question that was asked in the year 1982, and it states that in Young's double slit experiment, the interference pattern is found to have an intensity ratio between the bright and dark fringes as 9. This implies that. So we have to make sure it's a multi-correct option. So we have to find out which of these options will be correct. So option number A and B are respectively about the intensities only, and option C and D is about the amplitude ratio. Okay. And we are given that the ratio of the bright and the dark is given as 9. Okay. So it means ratio of the intensity maximum and intensity minimum is given as 9. Okay. And so we start from there only. So we are given that I maximum and the ratio I minimum is equal to 9. Okay. And maximum and minimum can also be written as the ratio of the intensity of the two sources, okay, or we can say two slits, and that comes as square root of I1 plus square root of I2 and its whole square, and the denominator is our square root of I1 minus square root of I2 and its whole square. And here I1 and I2, these are the intensities due to two sources. These are the intensities due to two sources, and we can just solve this particular equation now. Okay. And we can write this as square root of I1 plus I2 whole square is equal to 9 and I1 minus square root of I2 and whole square. So in the simple, we can just simplify it. We can write this as I1 plus I2 is equal to 3 times square root of I1 minus 3 times square root of I2. And this gives us, so we can write this as square root of I1, we have 1 minus 3, and other side we can write this as square root of I2 will be equal to -3 minus 1. So on the left side we get this as minus of 2 square root of I1 is equal to minus of 4 square root of I2, and here minus this 2 goes by 2, and this gives us that our square root of I1 is equal to twice square root of I2. So therefore we can write its ratio. This is I1 square root I2 is equal to 2, or we can say our I1 ratio I2 is equal to 4. Okay, so we found out the ratio of their respective intensity of the two sources. Okay, and so option number B is the correct one because it is 4 unit to 1 unit. Okay, so from here we can say option B is correct. Option B is correct. Now second, we have to find out the amplitude ratio. And for this amplitude ratio, we know that intensity is proportional to the square of the amplitude. So we know that our intensity, that is our I, is proportional to square of the amplitude, that is our A square. So therefore we can write it as I1 upon I2 is equal to A1 upon A2, and we are supposed to find out the I1 upon I2. We know, sorry, it is square. Okay, so from here we can say that our A1 upon A2 will be equal to square root of I1 upon I2, and ratio of I1 upon I2 is 4. So this comes as square root of 4. Therefore it gives us that the ratio of their amplitude is equal to 2. So option number D is the correct one. So you can see option D is correct. We start with the next question. And the next question, it was asked in the year 1982, and it states that a convex focal length of focal length 40 centimeter is in contact with another concave lens of focal length 25 centimeter. The power of the combination is. Okay, so we have to find out the power of the combination. And we know the formula. When the two lenses are in contact, then the total power, we can say the total power that our PT of two lenses in contact, we can write this as PT is equal to power of the convex lens plus power of the concave lens. Okay. And here we are given their focal length, and we also know the relationship between the power and the focal length. So we can say that power of the lens, that is our P, is equal to 1 upon its focal length, which is 1 upon f. So therefore, we can write this particular formula for convex lens as well as the concave lens. So we can write this for convex lens. We can say power of convex is equal to 1 upon focal length of convex, and this is our, it is given as 40 centimeter. So we can write this as 1 upon 0.40, and this comes as 2.5, and it will be, the unit will be diopters. Similarly, we can write for concave lens, which gives power of concave will be equal to 1 upon focal length of concave, which is equal to 1 upon, and this is our 0.25, but for concave it is a negative sign, so put it in negative, and this comes as -4 diopters. Therefore, the power combination, that is our P total, will be equal to 2.5 plus minus of 4, and this gives us -1.5 diopters. So this is the combined power, and the option, the correct one is -1.5. So option A is correct. Option A is correct. We come to the next question, and here it is asked that, it was asked in the year 1982, and it states that the screen S is illuminated by 2-point sources A and B. Another source C sends a parallel beam of light towards the point P on the screen as in figure. Line AP is normal to the screen, and lines AP and BP and CP are in one plane. The distance AP and BP are 3 meter and 1.5 meter. The radiant power of sources A and B are 90 watt and 180 watt respectively. The beam C is of intensity 20 watt per meter square. Calculate the intensity at point P on the screen. So the figure given to us, we have this point P, and it is being illuminated by 3 sources, A, B and C. B and C are at an angle of 60 degree with horizontal, whereas this source A is at a, we can say, 90 degree. Okay. So the source of A and B is given as 90 watt and 180 watt, and the beam from C, it is given as intensity in terms of 20 watt per meter square, and we have to find out the intensity at point P. So let us start with the given information. We are given that we have source A, and source A, its radiant power that is our PA, it is given as 90 watt, and distance from point P, distance from P, that is of AP, it is given as 3 meters. we have our source B, and source B, its power PB, it is given as 180 watt, and the distance, that is our BP, it is given as 1.5 meter, and it is at angle, and we can say the angle of incidence, is at the angle of a 60 degree. And we have third source, that is source C. The source C, its intensity is given. Okay. For source A and B, a radiant power is given, but for source C, intensity is given. So we can say intensity at point P, which is of IC, that is given as 20 watt per meter square, and it is also at an angle of 60 degree. Angle of incidence, it is about 60 degree. Okay, and we have to find out the total intensity at point P. So we have to find out the intensity due to source A and intensity due to source B, and for source C the intensity is already given to us. So let us start with source A. So we say intensity due to source A. Intensity due to source A, and source A is at a perpendicular to point B. So we can write this as intensity is our IA, that will be equal to its radiant power divided by 4 pi r square, and radius is given to us 3, so we can write this as 90 divided by 4 pi, and it's 3 whole square. So we can write this as 5 upon 2 pi watt per meter square. Similarly, we are going to find out intensity due to source B. Please keep in mind the source B is at an angle of 60 degree. So we have to make a correction for that. So we have intensity due to source B. Therefore, we can write that our IB is equal to its radiant power divided by 4 pi r square and multiply by the angle, that is cos of 60 degree. Okay. So therefore, we know 180 and divide by 4 pi, and r is our 1.5 whole square, and this comes as 1/2. So this comes as 10 upon pi watt per meter square. And we have to find out, this is our A, B, and now we come to the C. And C is, you can say, is same adjustment is required for the intensity due to source C. Intensity due to source C. So we can write our IC, and it is given as 20, and we are simply going to multiply this by cos of 60, and this comes as our cos 60 1/2. So this will be 10 watt per meter square. So total intensity at point P, we get this as I total will be equal to intensity because of A, intensity because of B, and intensity because of C. So we have 5 upon 2 pi plus 10 upon pi and plus 10. And we can simply solve them. We are going to get that our total intensity is approximately equal to 13.98 watt meter per meter square. So this is our total intensity. Yes, so it was a next question. It was asked in the year 1991, and it states that in Young's double slit experiment, the separation between the slits is halved and the distance between the slits and the screen is doubled. Then the fringe width is. Okay. So we know the basic formula of a fringe width. Fringe width is represented as beta. Beta is equal to lambda capital D divided by small d, where this capital D is the distance from the slits to the screen and small d is the separation between the slits. So we can write our fringe width, that is our beta, is equal to lambda capital D by small d. And we can draw an approximate diagram for that also. So this is our first slit, and this is second slit, and this is our screen. So distance between the screen is given as capital D, and this width is our small d. Okay, and lambda is the wavelength of the light used. And it is said that separation in slit is halved and distance between slit and screen is doubled. So let us say that new fringe width represented as beta prime, this will be equal to lambda d prime oblique small d prime, and this capital D prime is equal to twice of original distance, and small d prime will be equal to half of original distance. Okay. So we substitute it, we get our beta prime will be equal to lambda, and this comes as 2d divided by d by 2, and we can write this as 4 lambda d by d, and this comes as our 4 times beta. Okay. So new fringe width, that is beta prime, will be equal to 4 times the original fringe width. Okay. So we can say it has quadrupled. So option D is correct. Option D is correct. We come to the next question, and here it is asked in the year 1981, and it states that the convex surface of a thin concave convex lens of a glass of refractive index 1.5 has a radius of curvature of 20 centimeter. The concave surface has a radius of curvature of 60 centimeter. The convex side is silvered and placed on the horizontal surface. Okay, so based on this, we have two questions based on it. In the part A, it states that where should a pin be placed on the optic axis such that the image formed is at the same place. And in the part B, it states that if the concave part is filled with water of refractive index 4/3, find the distance through which the pin should be moved so that the image of the pin again coincide with the pin. Okay, so in both the cases, we can say the object and the image should be coinciding. Especially in the second case, a water is added into the concave part, okay, whose refractive index is given as 4/3. So in this particular case, we can divide this entire discussion into, we can say, like into the two parts. Okay, so we can say that a silver colored concavo convex lens where light undergoes three transformations. That means it is going to pass through various combinations. Okay. So first will be the refraction through the lens. So first transformation, it will be refraction through the lens. Refraction through the lens. Okay. So which basically means that the light ray will be coming from the air. It is going to pass either through the glass in the first case or water in the second case, and then it will be again our glass. So this will be a refraction. Second, it is going to do a reflection, and in this reflection it is going to take place at a silvered convex surface. And finally, the third part will be refraction again. Through the lens. But we can say it will be through glass and into our air or glass, and then it will be water. So we can say this system is going to behave like a combination of mirror as well as lens. So we can write from here that the system behaves like a mirror lens combination. So first of all, in part A, it is without glass without lens, okay, or we can say without water, sorry. So in the part A, we are only having glass lens, that it is without water. So therefore, first is a refraction through the glass lens. Refraction through glass lens, and we can use lens maker formula, and which gives us 1 upon FL is equal to mu minus 1, and we have this is 1 upon r1 minus 1 upon r2, and we are also given that the refractive index is it's 1.5, so that is basically 3 by 2. So we can substitute it as 3 by 2 minus 1, and it is given as 1 upon minus of 60 minus 1 upon 20, and we can easily solve this, and this will be giving us that our FL will be equal to 60 centimeters. Next is our reflection at convex silvered convex surface. We have a reflection at silvered convex surface. Now here the convex surface now acts as a concave mirror. The convex surface acts as a concave mirror. So therefore we can write its focal length Fm will be equal to r upon 2, and that is our 20 upon 2. This gives us a 10 centimeter. Okay. And the mirror is, you can say, behind the lens. Okay. So it's acts from within. So from here we can say, or rather you can say, we are required to find out that the final image should coincide with the object. You can say for final image to coincide with the object, this is our major question in both the parts, with the object. So it means the image formed by the lens must be at the center of curvature of the mirror. You can say the image formed by the lens should be at the center of curvature, at the center of curvature of the mirror, Therefore we can write its distance, that is V, should be equal to minus 20 centimeter. Once again we are going to use lens maker formula, and we can write it as 1 upon V and 1 upon U is equal to 1 upon focal length, that is f of L, that is for the lens. Okay. And we know, we just found out our V, that is minus of 20, and this is our 1 upon X, and this will be our minus of X is equal to 1 upon 60. So here U is taken as X, so we are going to find out our X, and this gives us that our X should be equal to our 15 centimeters. Okay. So therefore, so this is the position of the object, which is our pin. So we can say pin must be placed 15 centimeter from the lens. From the lens for its image to coincide. In the part, you can say B, it is asked now the concave side is filled with water and its refractive index is given to us as 4/3. So in part B, we have the concave side filled with water. And the mu is given as 4/3. So now in this case, the concave face whose radius is of 60 centimeter now forms a second lens filled with water. So you can say that the concave face whose radius is our 60 centimeter forms a second lens. Second lens with water. Once again, we are going to find a refraction through the lens, water lens rather now. We can say that reflection through water lens and we can write that as 1/Fw, which is our water lens, will be equal to 4/3 minus 1, and we have this as will be our 1/infinity minus 1/60, and this comes as our 1/80. Okay. Now we have combination of two lenses, water plus glass. Now we have to find out their effective focal length. Next is our combined two lenses. Combined two lens, one is our constituted because of the water and another one is from the glass. So therefore the combined focal length and let us call that as f prime. So you can say 1/f prime will be equal to 1/Fw plus 1 our lens. So this comes as 1/180 plus 1/60, and this gives us that f prime will be equal to 45 centimeters. Now the reflection at the mirror, it will be unchanged because there is no change in the mirror configuration. So you can say reflection at the mirror is unchanged. So now in this case, the light that emerges from the mirror as it is reflected from the concave mirror, which is radius of 20 centimeter, that we can say focal length of 10 centimeter. And once again, in this case also, we want that image of this entire combination should again fall at the same point where the object lies. Okay. So you can say that the concave mirror, its radius is given as concave mirror, its radius is given as 20 centimeter. So therefore its focal length is equal to 10 centimeter because nothing has changed in it. And once again we want that image to fall at the same point as the object. So we can once again write the formula, and that gives us 1 upon v minus 1 upon u is equal to 1 upon combination focal length, that is f prime. And we get this as 1 upon is our minus of 20. Let us suppose we call this as our now x prime is equal to 1 upon 45. So this gives us that our x prime should be approximately equal to 13.85 centimeters. So therefore the shift that is required in the object position, shift required in object position let us suppose that is delta x. So delta x will be equal to x minus x prime, and we have this as x we found out is our 15 centimeter. So we can say this is our 15 minus 13.85, and this can be approximately equal to 1.15 centimeters. So therefore the pin must be shifted by 1.15 centimeters towards the lens, to restore the coincidence. Next question. It was asked in the year 1981, and it states that a glass prism of refractive index 1.5 is immersed in a water of refractive index 4/3. A light beam incident normally on the face AB is totally reflected to reach BC if. So we have this figure, and we have the water whose refractive index is 4/3 and prism whose refractive index is 1.5, and it states that a light beam incident normal on the face AB. So we have a normal on the face AB, so it will be going something straight, and then it should be total internally reflected such that it reaches face BC. So it will be something like this, and let us suppose this is point B, and if this is angle theta and this is 90 degree, so this angle will be also our theta, because this angle will be 90 minus theta, so this is 90 and this comes as our theta. So we have to find out this value of theta, or we can say sine of theta. And in this case we are going to use Snell's law, as Snell's law states that our n1 sine of theta 1 is equal to n2 sine of theta 2. And because we require total internal reflection, so theta will be called as a, you can say, critical angle, that is theta c. Okay. And you can say that critical angle that is our theta c for total internal reflection it is given as theta c is equal to sine inverse of n2 upon n1. Okay. So we already have n2 and n1, so we can simply substitute the values. We get this theta c is equal to sine inverse of n2 is our, because of the water, that is 4 by 3. Okay, so let me write it here, because of the water, and this is because of the glass. So we substitute the values. Sine inverse, we have this as 4 by 3, and here we have it as 3 by 2. And this gives us sine inverse, we have 4 by 3 multiplied by 2 by 3, giving me sine inverse of 8 by 9. Therefore, for total internal reflection, for total internal reflection, our sine of theta should be greater than or equal to 8 by 9. And the option number A is the correct one. Option A is correct. We come to the next question. And this question was asked in the year 1979, and it states that what is the relationship between the refractive index of mu1 and mu2 if the behavior of the light rays is as shown in the figure. And if you compare both the figures, we can clearly see in figure, let us suppose this is 1, okay, light ray travels, you can say, in a straight line from one end to the other end, whereas in the figure 2, the light ray in the second end basically diverges. So it is because of the divergence behavior. So therefore, for the first, we can say that our mu1 should be equal to mu2, and for the second part, our mu2 should be greater than mu1. So this is the basic characteristic. Because of this, the behavior of the lens. Next question, it was asked in the year 1978, and it states that a pin is placed 10 centimeter in front of a convex lens of focal length 20 centimeter and made of material of refractive index 1.5. The convex surface of lens farther away from the pin is silvered and has a radius of curvature 22 centimeter. Determine the position of the final image. Is the image real or virtual? So, we are given that we have a convex lens and its focal length is 20 and refractive index 1.5, and the convex lens surface rather, which is further away from the pin, is silver colored. So we can say that we can draw approximate figure for that. Suppose this is our lens and principal axis, and somewhere here is our pin, and this pin is kept at a distance of 10 centimeter. So this distance is our 10 centimeter, and the surface is silvered. So this is our silvered surface. So this surface is silvered, and basically now it comes as a, you can say, the convex surface is silvered, so it will be now a mirror lens combination, okay, because silvered surface is now going to act as a mirror. So you can say that the convex surface is silvered, therefore it forms a mirrorless combination. It forms mirror lens combination. And we have to find out the final position of the image, and from the mirror surface it is quite obvious that the image will be formed somewhere to the left of this entire figure. And so we can say when the light comes from the object, it is going to pass through the lens, something like this, and then it will be reflected from the, you can say, the silver color, and it is going to pass again through the lens, and somewhere here, let us suppose it is going to give us a, let me draw it a straight line. So it will be something like this. So let us suppose this is our object and this is our image. So the sequence of this entire, we can say that the sequence is, first it is our lens, then it comes as a mirror, and then again back to the lens. So this entire sequence. And first of all, we are going to find out the power of the lens. Focal length is given to us, so we can find out its power. Or we can say, let us start with the focal length of the mirror, which is formed by the silvered convex surfaces. So we say focal length of mirror formed by silvered convex surface, formed by silvered convex surface, and we can write its formula. Focal length of the mirror will be radius of curvature and divided by 2. Radius of curvature is given as 22 divided by 2. So this gives our focal length of the mirror is our 11 centimeter. Okay, and it is a concave mirror, so we can just add a negative sign to it. Now we are going to find out what will be the effective focal length of the entire process. Process means lens, mirror and lens. Okay. We can say that effective focal length of combination and let us suppose that is our capital F. So 1 upon capital F will be equal to twice into focal length of lens plus 1 upon focal length of mirror. Okay, because lens comes twice, once from the incoming and another from the return part. And we can write this as twice into 1 upon 20, and this comes as plus, and this is 1 upon 11 with a minus sign. So this gives us that the focal length, effective focal length of the entire system is 110 centimeters. We have to find out the position of the image, and we can use the formula, standard formula, that is 1 upon V plus 1 upon U is equal to 1 upon F. Okay, and U is our minus of 10 and focal length we just found out is our 110. So we can say it is 1 upon V is equal to 1 upon F minus 1 upon U. This gives us 1 upon 110 minus, and this will be 1 upon 1 by 10, and that will be minus. So this gives us that a V is equal to minus 11 centimeters. So therefore this distance will be of our 11 centimeters, and the image will be virtual, 11 centimeter and virtual image. We have a virtual image. So we come to the next question, and in this question it is asked that, yes, it was asked in the year 1979, and it states that the radius of curvature of the convex face of the plano-convex lens is 12 centimeter and its mu is 15. Okay, so we have basically 4 questions based on this. First is find the focal length of lens. The plane face of the lens is now silvered. In part B, at what distance from the lens will parallel rays incident of the convex lens converge? And part C is the sketch the ray diagram to locate the image when the point object is placed at the axis 20 cm from the lens. And part D, calculate the image distance from the object placed in the C. So this is, we can say, we can divide this entire discussion into 3 parts. First is a simple plano-convex lens. Second, when the plane lens is silver colored. And third, we are going to solve it for the actual solution based on the part B. Okay. So we can use to find out the focal length of the lens. So let me, okay, we can say focal length is our 1 upon F is equal to mu minus 1 upon R1 minus 1 upon R2. And initially the lens is something like this. So radius of curvature for one side will be infinity, another side it is already given as to 12. So we substitute it, we get 1 upon f is equal to 1.5 minus 1, and this 1 upon 12 minus 1 upon infinity, and this gives us that focal length is our 24 centimeters. So it means the lens is converging with a focal length of 20 more centimeters. The lens is converging with the focal length of 24 centimeter. Now we come to the part B, where this plane surface is silvered. So initially the lens was like a simple one. Now here it is the plane surface is silvered. So this surface is now silvered. So you can say that when plane surface is silvered, plane surface is silvered. Now this combination, or we can say the entire system, is now going to act as a lens, mirror and back as lens. So we can say the system acts as a lens, then it will be our mirror, and then once again it will be our lens. And we are supposed to find out focal length of lens, plane surface is now mirrored. Okay, so therefore we can find out its focal length, and so under this combination we can say the power of the system, that is our P, will be equal to PL plus PM and once again our PL. So therefore we get P is equal to twice PL and plus PM, and PL is equal to 1 upon FL, and this is 1 upon 0.25 meters, and this gives us 4.17 diopters. And for plane mirror, that is a PM, that will equal to 1 upon infinity, and this gives us 0. Therefore total power P is equal to 2 into 4.17, this comes as 8.33 diopters. And now we can find out the, you can say, focal length, that is our capital F is equal to 1 upon P, and this gives us F is equal to minus of this 8.33, so therefore F is approximately equal to minus 0.12 meters, or we can say approximately equal to 12 centimeters. So therefore the silver color lens now acts as a concave mirror of focal length 12 centimeters. So we can say the silver lens acts like a concave mirror of focal length 12 centimeter. And we have to find out, you can say, position also. So therefore we can say that for parallel incident rays, our u will be our infinity. Okay. So therefore we can write 1 upon v plus 1 upon u is equal to 1 upon f, and this gives us 1 upon v is equal to minus of 1.12, giving us that v is equal to minus of 12 centimeters. I think this was for parallel incident rays. Okay. And therefore we can say the parallel rays converge at 12 centimeter in front of the lens. It means on the same side because of the negative sign. You can say parallel rays converge centimeter in front of the lens. And for that we can also draw an approximate figure, and that figure will be our something like this. We have a silvered lens, and one of the surface is silvered, and we have this as a principal axis, and we are given that the rays are coming from infinity, so it will be coming from something like this. And if without the silvered, it will be in this direction. So let us call this as image 1. Now this will be acting as a virtual object, and we are going to have this will be our I1, and this is our I3, and the distance is about 12. And let me draw it as solid one. So in this direction, and because of this virtual thing, that I1, it will be forming like this. So this will be our I2. So I2, I3 as well as I1. And in the next part, we are supposed to find out ray diagram, locate the image when the point object is placed on the axis 20 centimeter from the lens. Okay. So now we come to the next part, which states that for an object at 20 centimeter in front of the lens, in front of the lens. So basically u will be our minus of 20. So once again, the basic formula 1 upon v plus 1 upon u is 1 upon f, and this gives us 1 upon v minus 1 upon 20 is equal to minus 1 upon 12. So we get that our V is equal to minus 30 centimeters. So image is formed 30 centimeter in front of the lens. Image is formed 30 centimeter in front of the lens. And we can just draw the figure for that. And the object is our at 20 centimeter. One second, it is 20. Yeah, 20, and we have to draw the ray diagram for that. Okay. So we can draw an approximate figure for that also. The surface is silvered, and this is our principal axis, and it says that our object is at 20 centimeter. And this will be resulting in a formation. Let us suppose this is object, and this will be our I2, and here we are going to have our object, and this is our I1, and this is our I3. Okay. And we are going to get this as a 30 centimeter, and this is our 20. Okay. So this is approximate diagram for this. Next question. It was said that, it was asked in the year 1978, and it states that a ray of light incident at an angle of 60 degree on one of the face of the prism, which makes an angle 30, which has an angle of 30 degree. The ray emerging out of the prism makes an angle of 30 degree with the incident ray. Show that emergent ray is perpendicular to the face through which it emerges, and calculate the refractive index of the material of the lens. So first of all, we are going to draw the basic figure based on this, and then we are going to prove or find out whether the emergent ray is actually perpendicular to the face through which it emerges. And in our basic diagram, let's draw the prism, and this is our angle of the prism, that is usually represented as A, and we have an incident ray. This is normal to the surface, and it's supposed bend like this, and here also we have a normal to the surface. And one second, they are going to meet somewhere like here. So let me extend the prism, and then this is going to bend in this direction. So we have this as angle of incident. This is first angle R1, this is single angle R2, and we have an emergent angle E, and the deviation is the point where incident ray and the refracted ray meet each other. So this is our angle of deviation, that is given as delta. So this is the basic figure about the, you can say, it has to be a straight line actually. So this is a basic figure of this prism along the incident ray as well as refracted ray. And then we have to try to find out whether the emergent ray, means this ray, is coming perpendicular to this face. This is our final question which is asked. So in this particular description, we are given that the incident angle is of 60 degree, and angle of the prism, that is of A, is our 30 degree and deviation is also 30 degree. Deviation is also our 30 degree. Okay. And we know the relationship between the emergent angle of prism and deviation. So we have that our I plus E is equal to A plus delta. And also we have a Snell's law which gives us that mu is equal to sine of I and divided by sine of R1. And we can say for inside of the prism, we can also write that our A, that is angle of prism, is equal to R1 plus R2. So first of all, we are going to find out what will be our angle of emergence, and that is going to tell us that how the question is to be, whether it is perpendicular or not. So using these formulas, so we are going to use first formula, that is I is equal to E A plus delta, and we have this as 60 plus E is equal to 30 plus 30, and this gives us that angle of emergence is equal to 0 degree. Okay. So it means the angle of emergence is 0 degree, that is the emergent ray is perpendicular to the emergent face. And what else we have to find out? We have to find out the refractive index also. Okay. For refractive index, we should be knowing what is our R1, and we can use that our emerging angle is equal to 0. Therefore, we can say our interior angle R2 will be also equal to 0. And this gives us that our A, which is equal to R1 plus R2, this gives us that our R1 is equal to A, and which is our 30 degree. Okay. Now once again we are going to use Snell's law, which is our mu is equal to sine of incident angle. Incident angle is of 60 degree, and sine of the R1 is our 30 degree. This gives us root 3 by 2 and divided by 1 by 2, giving us that refractive index is root 3 of. And we can also draw the figure for the emergent ray when it is at a angle of perpendicular. So we can just draw the figure. Once again we are going to have a triangle, and the incident angle, and here after that it is straightforward, is going to pass like this. Okay. And this is our angle of incident, and we are going to have this as R1, and here if we extend this part, this will be our deviation, that is our 30 degree. Okay. And this angle is given as 30 degree. So we come to the next question, and here it is asked that it was asked in the year 1978, and it states that an observer can see through a small hole on the side of a jar, radius 15 centimeter, at a point at a height 15 centimeter from the bottom of C figure. The hole is at a height of 45 centimeter. When the jar is filled with liquid up to the height of 30 centimeter, the same observer can see the edge at the bottom of the jar. If the refractive index of liquid is n by 100, where n is integer, then the value of n is. So we have to find out value of n. In this case, this is a basic figure given to us. You can clearly see that when there is no water, the person can see at a height of 15 centimeter. And when we add water to it, the person can see the bottom of this you can say tank. So therefore, we can just try to modify the figure and let us draw a normal to it. And if water is, one second, the hole is at 45 centimeter, and okay, water is filled at a height of 30 centimeter. So water is suppose is filled at a height 15 centimeter, correct. So water is filled up till this point. So this is our 30 centimeter, and as soon as water is filled, we can clearly see it is going to do a refraction and come to the bottom, something like this. And then we are going to have, this will be our, because the light rays will be traveling in opposite direction, so we are going to have this as angle of incident, and this will be our angle of refraction. And we are given the total height is of 45 degree, and this is of 30 degree, and this is of 15, and therefore this height will be also over 15 centimeter. Okay, so this is 15 and this is 15, so we can make this angle will be of our 45 degree, because this is our 15, so this is our 45 degree. So this is the basic diagram, and we have so we can find out the angle of incident is inside the water, that is our I. We can say that angle of incidence in liquid, that is our I, and the angle of refraction is in air, that is our R. Angle of refraction is in air, and that is our R. Okay. And the vertical height of the water from the bottom is given as 30. Height of liquid, it is given as 30 centimeter, and the horizontal displacement is given as, you can say, 15 centimeter. Horizontal displacement it is given as 15 centimeter. So we can write that our tangent of our I is equal to 15 by 30, and this is our 1 by 2. So therefore we can say our I is equal to tangent inverse of 1 by 2. Yeah. And we can now apply Snell's law at the liquid air boundary. Snell's law at liquid air boundary. we can say that our refractive index of water, let us suppose that is our NW, and we have sine of I. Liquid index of the air, let us suppose is Na, and that is our sine of R. The index of refractive index of air is 1, so we can directly write it as sine of R. And from the geometry, we can say that so we found out this is our angle 45, this is 90 degree. Okay, so this angle will be also, sorry, this small angle will be also our 45. So we have vertical opposite angle, so our R will be also equal to 45. So we can say from geometry, we can write that tangent of our, let me straightforward write it. From the geometry, we can say that our R will be equal to 45 degree, and therefore we can say that our sine of R we found out is 45 degree, and which is our theta 2. 1 second. Yeah, so we have to find out the refractive index of water. Okay, so we get this as refractive index of water into, this is our sine of incident angle. Okay, we have to find it, we don't know it. So we can say that sine of our refraction, that is our R, will be equal to, we can write that as 1 upon square root of 2, and we also know that our incident angle I is equal to tangent inverse of 1 by 2. So we can say from here that our sine of I will be equal to 1 upon square root of 5. Okay, and now we substitute the values. So we can say refractive index of water into 1 upon square root of 5 is equal to 1 upon square root of 2, and this gives us that our refractive index of water is equal to square root of 5 divided by 2, and this comes approximately equal to 1.58, and we are given that the refractive index is n by 100. You can say it is given as n by 100, so this will be equal to 1.58, giving us that n is approximately equal to 158. So these were the questions which was asked the year 1978, 1979, 1981 and 1982. So we are having total number of 11 questions from all these 4 years. So this complete all the questions. Thank you.